Hey, welcome back. Today we're going to be talking about line integrals, which are a new type of integral. It's going to use our knowledge of vector fields and of parametrized curves. So let's do this. All right, so here is our motivating question for today. We have a vector field. It's the vector field 1, comma, negative xy. It's the one that's shown in the picture here. And the question is, if this is a vector field describing a force, meaning that at every different point in the plane we're experiencing a different force based on what the value of the vector field is there, and we're moving along the top half of the circle of radius 1. So here's that. As we move along this circle, how much work is done by the force field described by this vector field? Just as a reminder, we computed work a while back when we were talking about vectors for the first time by taking the dot product of a vector that was describing a force and a vector that was describing a displacement. But the important thing to note is this only works if the force is constant. And as we're moving along this semicircular path, the force changes based on where we are. So we're not going to be able to just take a dot product and maybe we already kind of see the pattern here. That's why we're going to be using an integral to solve this problem, because we have a computation that we'd like to be doing, but it only works when the things involved are constant. So that's why we're going to use an integral. Other thing to note is that there's actually not enough information here to completely answer this question, because if we walk along this path from left to right, starting on the left side and moving to the right, we're walking kind of more in the direction of the arrows than against them. So we expect the work to be positive because the force is mostly pointing in the direction of our displacement. On the other hand, if we walk from left to right, the work would be negative because we're mostly going in the direction opposite of the force. So what that means is we actually need to provide a little bit more information to make this a well-founded question. So let's just say for this one that we're going to move along the top half of this circle of radius 1, starting at the right. So from the point 1, 0 to the point negative 1, 0. This will be kind of one of the things that we'll need to keep track of when we're talking about line integrals, is that the orientation always matters. So what we've provided, this is specifying an orientation on the path. And it's saying we're going this way. We're moving along the path from right to left. Okay, so as you might expect for a problem that we're solving with an integral in our class, it's going to involve taking this thing that we're integrating over this path, slicing it into pieces. On each piece, we're going to approximate the work done, and then we'll add all of those approximations together, take a limit, and then we'll end up with an integral. And actually, some of the stuff that we're going to, some of the ideas. And actually, some of the ideas that we're going to use here are also things that we use in the certain. And actually, some of the ideas that we use here are things that we used back a couple days ago when we were talking about scalar surface integrals. So the first thing that we're going to want to do is slice this curve into pieces. But actually, and kind of similarly to how we proceeded for scalar surface integrals, the first thing we're really going to want to do is parameterize the curve, which I'm going to call C, by the way. C is the name of the curve. Then we're going to slice. So just a note over here, the parameterization that we'll use, it's a circle of radius 1. So we'll use the parameterization using sines and cosines. And we only have the top half of the circle. So let's just note the parameterization domain is all t between 0 and pi. So what we're really going to do is we're not going to slice the curve, strictly speaking. We're going to actually slice the parameterization domain. So we're going to slice the interval from 0 to pi into segments of length, and let's call the length delta t. So here's the parameterization domain, here's 0, here's pi, and we're going to come in and cut it into pieces. So just so that the picture doesn't get too messy, I'm going to cut my interval into just 6 pieces. The spacing between them we'll call delta t. But we just want to be able to work in the parameterization domain, sort of like how we did with scalar surface integrals. The integral is actually going to be something that we're computing in the parameterization domain, and we'll use the parameterization to kind of connect what's going on in this interval from 0 to pi to what's going on over this circle. Something we want to remember, though, is that the parameterization is a function that's taking this interval from 0 to pi and transporting it onto this curve, giving us a way to connect points over here to points on the curve. The next step is the approximation step. So we want to approximate the work done over each segment. So what we're going to do is let's just look at one particular segment. Let's look at the segment of the curve between this green point and this green point. So if we've cut our curve into small enough pieces, then we can assume that over this segment here, the vector field is constant and its value is equal to whatever the vector is at this point here. So first of all, let's just give a name to this point. This is going to be t, and that makes this first green point r of t. Let's say that the vector field vector at this point looks like this. This vector is the vector field evaluated at the point here. So this is the vector f of r of t. And so to approximate the work, remember the work is approximately going to be the force dotted with the displacement. In this case, the force is, well, we are assuming that it's f of r of t over that entire segment, whatever t is here. To figure out what the displacement is, though, we need to do a little bit more work. And for the displacement, well, we're moving along the path from this green point to this one, so the displacement vector is going to be this vector here. So this is where things are going to be similar to what we did in the scalar surface integral video, because we want to figure out a nice expression for this green vector, because that's what's going to go here for the displacement. What we did is we're drawing the vector that starts at r of t and goes to this point. Well, this other point is what we get if we start at t and advance by delta t. So here, over here we have t plus delta t, which means that the second green point is r of t plus delta t. And so the displacement vector is, well, it's exactly r of t plus delta t minus r of t. But if you remember, we had something similar in the scalar surface integral video where we approximated this vector, noting that it's the change in the output of a function as we change one of the inputs by a little bit, by delta t. We're going to approximate that by r prime of t delta t. Again, if you want a more thorough explanation of why this approximation makes sense for the displacement vector here, this green vector, go check out the scalar surface integral video. We're now ready for the last two steps of our integral process. We're going to take all of these approximations and add them together. So the total work done is approximately the sum of those approximations over each piece, f of r of t dotted with r prime of t delta t. And you know I'm never too precise with this summation notation. Let's just say we're adding up one of these things for each segment. Lastly, we'll take a limit, noting that if we were to take smaller delta t's than in the picture that we had before, the spacing between these segments would be smaller, and so we would be approximating the vector field by a single vector over shorter intervals, and so we'd expect our approximation to get better. So the total work we'll find by taking a limit as delta t goes to 0 of these approximations, which I forgot to note, these are Riemann sums. And the limit that we'll get will be an integral. It's going to be an integral over the interval that we slice into pieces, which for this specific example was the interval from 0 to pi. And the function that we're integrating is this f of r of t dot r prime of t, and then we have a dt. So this here, that is the formula that we'll use to compute line integrals. Now that we have that formula, let's actually use it to compute the line integral that solved the problem from earlier. Remember, the vector field in question was 1 comma negative xy, and the curve, which we called c, was the circle of radius 1, just the top part. And again, we need to note the orientation from right to left. Remember that we wanted to compute the work, which is going to be computed as a line integral. And I didn't say this earlier, but the notation for line integrals in general, we write an integral, the curve is a subscript, and we write the vector field, which in this case is f, dot dr with a vector hat on the r. So that's just the notation. And the way we compute it, again, is going to be this integral over whatever interval you parameterize it of f of r of t dot r prime of t dt. Again, this is how we compute it. Over on the side here, let's just compute the things that we need to write down this expression. Remember we wrote r of t is cosine t comma sine t, and so r prime of t is going to be negative sine t cosine t, just taking derivatives of each term. And then f of r of t, that'll be the vector field that we get by plugging in the x and y components of our parameterization. So this is x and this is y into the vector field up here, wherever we see x and y. So f of r of t will be the vector field 1 and then comma negative x times y. X is cosine t and y is sine t. So we'll have cosine t sine t. And so the integral that we'll get is an integral from 0 to pi. F of r of t is 1 negative cos t sine t dot r prime of t, which is negative sine t comma cosine t dt. To keep going with this, we should expand the dot product. So we'll get the integral from 0 to pi, and then we'll expand this dot product. We'll get 1 times negative sine t, and then plus the product of negative cosine t sine t and cosine t, which will be negative cosine squared t times sine t dt. I'm not going to keep going with this, but this is definitely an integral that you could compute to finish this problem. All right, so one last thing. If we go back to that original problem, we made a choice of orientation of the path. We were asking, what's the work done if we move along this curve from left to right, starting at the point 1, 0 and ending at the point negative 1, 0. But we could also have asked, what if we go the other way? What if we started at the left and moved to the right? It comes down to, well, if we're talking about work and the force stays the same, but the displacement is negated, meaning we're going in the opposite direction, well, just from this formula, you can see that that would just negate the work done. So the way that we'll express that using line integral notation is that if we were to do a line integral and the curve that you were integrating over was the same curve that we started with, but with the opposite orientation, then what we get would be the same number, the same line integral, as if we hadn't reversed the orientation. The only difference is that we would have a minus sign here. So in other words, reversing the orientation of the curve negates the line integral. So that's the end of the introduction to line integrals. In your next class, you'll do some practice problems that have you computing line integrals, and you'll also get some practice with qualitatively figuring out what a line integral should be based on a picture for a vector field. So that's the end of this one. I'll see you next time.